This is the review of the practice test for the physical science final exam. Temperature is a measure of the average what of the particles in an object. That would be kinetic energy. Okay, we measure temperature, or we look at temperature as being the faster the particles are moving, the hotter it is, or the hotter it is, the faster the particles are moving. It works both ways. So something that's very cold, the particles aren't moving very much. That's when you end up with a solid. When the particles are moving really fast, you end up with a liquid or a gas, and the temperature is higher. So that's how that works. That's the kinetic theory of matter. Thermal energy always goes from, well, the way to remember this is that heat or thermal energy always goes downhill. So energy always goes from higher to lower state. So if you put something hot next to something cold, the hotter object will warm up or transfer energy to the colder object until they end up at the same temperature, or it will try to. It doesn't always work, but it always goes from the hotter to the colder, or the higher to the lower energy state. A substance that allows thermal energy to move is called a conductor. That's true for electric energy as well. Things that move readily are called conductors. Things that impede or slow down the transfer of energy are called insulators. But a conductor, so we use metal pots and pans because metal is a good conductor of heat. Convection is the transfer of energy process that's conducted by the motion of fluids. Those could be liquids or gases, which are both considered fluid. So it doesn't just mean liquid. It could be warm air moving to heat up something in your oven or things like that, or just the warm air coming out of a heating vent. That process of the warm air mixing with the cooler air is called convection. Conduction, opposed to convection, conduction happens by contact, so it's a direct transfer, and when we look at it at the atomic and molecular level, what's actually happening is the really fast particles are crashing into the slower ones and transferring their energy, which eventually speeds up the slower ones. It slows down the faster ones as well, but you're actually taking molecules that are moving really fast and smacking them against ones that are moving slower, and that process transfers energy from one molecule to the next. That's conduction, direct contact. Finally, radiation is the transfer of thermal energy by, as the name implies, radiation. So this would be things like microwave or light heating something up. Okay, it's actually waves of energy that are transferring the energy from the radiation to the particles, which makes the particles move faster. This is how a microwave works. Microwaves make water molecules in food move faster, which raises the temperature of the food. That's the way a microwave heats up your leftovers. The transfer of thermal energy cannot happen without particles. This is not true because of what we saw in the last question. Thermal energy can be transmitted by radiation, okay, which radiation doesn't require particles in order to be transferred. If you're talking about conduction or convection specifically, those require particles because it's about the interaction of those particles transferring energy back and forth. But radiation does not take place or need to take place in the presence of particles. The Kelvin scale has no negative values because 0 Kelvin is absolute zero, the coldest theoretical temperature possible. There is no negative Kelvin. The amount of energy it requires to raise a certain amount of substance by 1 degree Celsius is called specific heat. Okay, all different substances have their own specific heat. So a low specific heat would be things like metals that you can raise the temperature easily. High specific heat would be things like water, which it takes a lot of energy to heat up water. If we were talking specifically about water, then you'd be looking at the calorie. A calorie is the specific amount of energy it takes to raise 1 gram of water 1 degree. So calorie is specific to water. but the term specific heat could be used for any substance. So that's what this question was asking. The difference between Kelvin and Celsius scale is 273. So Kelvin minus 273 equals Celsius, or Celsius plus 273 would equal Kelvin, either way. But the difference is each degree Celsius is equal to one increment on the Kelvin scale. It's just they start in different places. At absolute zero, particles will have zero motion. That's the theory, because we go back to the first question. Temperature is measuring the motion of particles. So zero temperature means zero motion, which is also why there's no negative Kelvin, because if you think of temperature as being movement, once movement stops, you can't have lower temperature because you can't have less than no movement. Substances begin to change from a solid to a liquid. That is known as the melting point. Okay, so you're going to want to know all these phase changes: melting, evaporation, freezing, sublimation, deposition, condensation. Okay, what those all mean, changing from one state to another, solid to liquid to gas and back. Those are all the changes that you'll need to know. We covered this a little bit in an earlier question. Thermal energy always moves to the lower temperature area, right? Lower energy goes from high to low, always. Thermal energy, how heat moves and work, is known as the law, or laws, really, of thermodynamics. Thermo meaning temperature, dynamics meaning change. The concepts, or actually the laws of thermodynamics, were summarized by Newton's laws of thermodynamics. When things get colder, they get smaller. That process is called thermal contraction. The change in substance from a liquid to a gas is known as, should have been more clear about this, you could have said either evaporation or boiling, and you would have been correct. They both fall under the umbrella of evaporation. Evaporation is any change from a liquid to a gas. Boiling is a specific point on the scale, right? If you heat something up to its boiling point, it evaporates. So in this case, either one of those would have been correct. On the actual final, it won't be ambiguous like that. It'll be a definite answer about boiling, freezing, sublimation, one of those. Going from a gas directly to a solid. So this is not condensation and then freezing. It skips over the condensation and goes from gas right to solid. That process is called deposition. Not a lot of substances do this, but certain things like dry ice, like carbon dioxide, iodine would be another one. They don't have a liquid state under normal conditions. They go right from solid to gas and back. A substate of matter with neither a definite volume nor definite shape, that would be a gas. Right? Gases can be expanded or compressed, so they have no specific volume. They can change shape to fit any container, so they have no specific shape. So solids have definite volume and shape. Liquids have definite volume but not definite shape, and gases have no shape or volume. So definite volume, but a definite and a definite shape, but no definite shape. Sorry, has a definite volume, does not have a definite shape. That's a liquid, right? Because liquids will fill around and change shape depending on what container you put them in, but you can't squish a liquid, and you can't put a half gallon of water into a 1 gallon bottle and have it fill up the bottle suddenly, take up a gallon of volume. It's still a half gallon. Most matter becomes less dense or expands as you heat it up, and condenses or gets smaller as you cool it down. The exception to that is freezing water. Ice is less dense than liquid water. That's a very rare circumstance, but if you think about it, ice cubes float in water, even though they're both made of water, And that's because when water freezes, the molecules actually form a sort of a network that ends up with a bunch of empty space in it, so it expands as it freezes. Most things, when they freeze, they become more compact, they condense or compress. An ice pack makes you feel cold because it does what? It absorbs energy, right? You might think, it's kind of weird, you might think that an ice pack makes you cold, and in a way it does, but the way it does that is because when you put a cold ice pack against your body, remember heat goes from hot to cold, so what's actually happening is your body is trying to warm up the ice pack. So the energy is going from your body to the ice pack. It's not like cold is coming into your body, it's actually the heat leaving your body that makes you feel cold. So ice packs absorb energy. The smallest part of an element that has that properties of that element is what's known as an atom. Right? If you break up an atom, then it's not an atom of that element anymore. You might end up with a smaller atom that's some other element, but you can't break an atom of an element into anything smaller without altering its properties. Mixtures can be elements, compounds, homogeneous or heterogeneous. Well, they can be either homogeneous or heterogeneous. Mixtures are not. They could be made up of elements, but elements are not mixtures and neither are compounds. Those are both examples of pure substances. Matter has blank properties that can be used to identify it. It has both physical and chemical properties. Physical would be things like color and density. Chemical would be reactivity, things like that. So we can use the combinations of physical and chemical properties to identify unknown substances. This is part 2 of the final exam review. When you separate mixture, what properties could you use to separate them? Shape, color, texture, or size? Well, you could actually use any of those. Right? You can use a filter to shift things by size. You could have some way of using the texture, if it's smooth or rough, to capture it. Visually, you can certainly look at color, and again, with certain filters, you can let, for example, round things go through, but not irregular shapes go through. An ice cube floats while sugar sinks. What can we conclude? Well, we already talked about the fact that ice is less dense. That's why it floats. And the reason the sugar sinks is because it is more dense, so that means actually both A and C are correct. If you have two blocks that both sink when placed in water, what can you say? Well, you could say that they're both more dense than water, but that's not a choice. You can't definitely say any of these other things, right? You don't have enough information to know if they're the same density. You just know that they're both more dense than water. One could be very dense and one could be just a little more dense than water. They both still sink. You can't say they have the same mass or the same volume because you don't know about the actual size. There's no information about the size of these objects, so you can't calculate the mass and you can't calculate the volume. And it doesn't say anything about the color, so you don't have that information. So the answer is E. When a liquid can dissolve more solute, we describe it as being unsaturated. So unsaturated means it could hold more. Saturated would mean it has reached its limit. And then there's another thing called supersaturated, which is exceeding its own limit. The measurement of the amount of solute that can be dissolved in a specific volume of solvent is the solubility. Okay? The concentration is measuring how much is actually in the solution. But if you want to know how much, for example, sugar could be dissolved in 1 liter or 1,000 milliliters of water, that number, let's say it's 100 grams, would be the solubility of sugar. It's the limit of how much you could dissolve. The amount that's actually dissolved is the concentration. Which of these is a pure substance? Well, pure substance means it always has the same composition, so it's always made of exactly the same stuff. The only one of these, you could make a case for sugar or distilled water, and I would have given you credit for either one of those. Again, on the actual test, it won't be optional. It'll be definitely one that's correct. If I wanted to pick the one that was most correct, I would say sugar, because even distilled water could still have some sort of impurities in it that would make it more of a mixture than a pure substance. But if you picked distilled water, I wouldn't have said you were wrong. A solid mixture in which the components are not easily distinguished. So when you have a mixture where you cannot tell apart the components of the mixture, that's called homogeneous or a solution. Those are both terms you could use. When you're specifically talking about a mixture of solids or a solution made up of solids, which we don't really usually think of, that would be called an alloy. So an alloy would be something like brass. Brass is not an element, and it's not a compound. It's actually a mixture of metals, or bronze would be another one, where you take a couple of metals, you heat them up, you combine them in the same container, and then you let them cool down, so you make this mixture. And if you slice it, you can't see the different metals without an electron microscope, but they're not actually chemically bonded, because if you heat them up again and let them cool down at different rates, you would be able to separate the copper from the tin, for example, if you're making bronze. So it's a mixture, not a compound, and if it's two solids where you can't tell them apart, that's called an alloy. The smaller part of a mixture involving at least one liquid would be called the solute. Right? The solute is the smaller part, or the part that gets dissolved. The solvent would be the larger part. So if you have salt, put it in water. The water is the solvent. The salt is the solute. The salt gets dissolved into the water. When a solid is added to a liquid and the solid disappears, we say that the solution has become more concentrated. Okay, that's all we can say. We can say if it's dissolved, that means you have now more stuff dissolved in it than you did before, and concentration is a measure of how much stuff is dissolved. So if you add more dissolved stuff, you increase the amount of concentration. A liquid mixture that does not separate after mixing would be a colloid. So a colloid is a special kind of mixture. Milk is an example of this. Milk is a mixture of mostly water with things like different types of fats and sugars and proteins mixed in. But because of the size of the particles, basically they're all bouncing around each other like ping pong balls. And because of this interaction, they can never settle. Like if you mix dirt in water, or soil or sand or whatever, you make muddy water. If you leave the water alone, the dirt will actually eventually settle to the bottom, right? Like it does in the ocean or in a river or something. But things like milk, which is a colloid, those particles are bounced around so much that they never really can settle to the bottom, so it stays mixed even if you don't mix it actively. If you just leave it alone, it won't separate. So basically you make a salad, you can still see the different parts. The parts are different and they're not necessarily evenly mixed throughout. That is the definition of a heterogeneous mixture, a mixture where the components are easily distinguished and where they're not necessarily evenly distributed is heterogeneous. Homogeneous is the other way around. Homogeneous mixture, you can't see the components anymore, like sugar in water, and they are evenly mixed. So the solution of sugar in water, it's not like you can pick out one corner of the cup of water and say, oh, there's no sugar here. The sugar is everywhere, spread out throughout the water. A mixture of and this should have said solid, suspended in a gas. That type of mixture is what's known as an aerosol. So certain combinations have special names like alloy or aerosol or gel, which is a type of suspension. But a solid suspended in a gas is called an aerosol. A compound can be made up of atoms of two or more elements. Compounds are never mixtures. And a compound isn't really made up of molecules. A molecule is made up of atoms. So it's kind of the other way around. That's why that wasn't the right choice. The nucleus in an atom in the center contains the protons and the neutrons, so that would be B and C. The major atomic particles are the protons, neutrons, and electrons. The mass is found in the center, and we call that very dense region the nucleus of the atom, which contains the protons and the neutrons. The small atomic particle with a negative charge is an electron. Electrons are negatively charged, and they're really, really tiny. A relatively large particle with no charge is neutral, that's a neutron. And finally, the large particle with the positive charge, that's the proton. Pros are positive, so proton is a positive particle. If an atom has a charge, that means that it does not have the same number of protons and electrons. Okay, when an atom has a neutral charge or no charge, that means that the protons and electrons are equal and they cancel each other out. But as soon as you change the balance of protons and electrons, you end up with a charged particle called an ion, which could be positive or negative depending on which particle has more than the other. If there's more electrons, it's negative. If there's more protons, it's positive. As you go across the periodic table, you have elements of increasing mass because they get bigger. Bigger in terms of the number of protons, electrons, and typically neutrons. Not necessarily bigger in terms of the radius or the sort of space of the atom. In the same column, elements have similar properties, and the reason they have similar properties is because they have the same number of valence electrons. So the correct answer is A and C, which is choice D. The element is organized based on properties and trends. Okay, so the columns are based on properties. Right? The elements in each column have similar properties, and then the reason that the elements are arranged as they are from left to right is because when you arrange them that way, you get predictable trends in terms of their properties like size, electronegativity, metallic or non-metallic. They're all wrapped up in the structure of the periodic table. The atomic mass that appears on the periodic table, so this is the one that's the decimal value that you see on every periodic table, tells you the average, it's actually a weighted average, of the mass of all the possible isotopes of that element. That's why it's a decimal, because it's an average. The mass of an individual atom is equal to the number of protons plus the number of neutrons. So how do we find? So it's protons plus neutrons. So if you know the number of protons, which remember the number of protons is the atomic number of the element, then that means that the atomic mass minus the protons equals the neutrons. So there's going to be questions where you might have to figure that out, and there's one coming up. So protons plus neutrons equals mass, which means mass minus protons equals neutrons. This is part 3 of the final exam review. Okay, isotopes are atoms of the same element with different, well, they have a different number of neutrons, which is not a choice, but because they have a different number of neutrons and neutrons have mass, that means that the mass of isotopes are different from each other. So they're all the same element, but they have different masses. An atom that is unstable, and the atoms are unstable because the protons and neutrons get out of whack, they will do different things to become stable, but all of the things that they do, which involve getting rid of particles and energy and things, that whole process is known as radioactive decay. Electrons are located somewhere in space outside the nucleus, but they aren't, or at least we don't, they move in random directions, but we don't consider them to be completely random in terms of their distribution. We have given them these spaces to occupy, and we call those spaces orbitals. So the regions of space that are occupied by electrons are known as orbitals. Which of the following statements is true about isotopes? All isotopes of an element have the same number of protons. Isotopes of elements have the same atomic mass, etc., etc. Well, if they are the same element, and they have to be the same element to be isotopes, they have to have the same number of protons, because the protons tell you what the element is. If they had different numbers of protons, they wouldn't be isotopes, they'd be different elements. And the first requirement of an isotope is that it's two atoms of the same element. So, any question about isotopes, you need to know that the protons are the same, but the neutrons are different in a pair of isotopes, right? When you're looking at two atoms side by side. First thing, do they have the same number of protons? Yes. Okay, that makes them the same element. Do they have the same number of neutrons? No. Well, then they're isotopes of whatever element that is you're looking at. If you're trying to compare a proton and a neutron, well, a proton and a neutron are the same size. Different charges, same size. Which of the following is the least accurate, or another way of saying that would be which is the most wrong or most incorrect comparison between the nucleus and the electrons? Well, in this case, you have to remember that the nucleus is super duper tiny compared to the space where the electrons fly around outside the nucleus. So if you're looking for the right example, you'd be looking for the one that has the biggest difference, right? Because the electrons are occupy a huge amount of space. Not the individual electrons; those are really tiny. But because they move around, the space, the cloud of electrons, is huge compared to the nucleus, which is really, really tiny. So in this case, we're looking for the one that has the worst example of that, and that would be actually this one, choice A, which in fact has the orbitals, the electrons, being smaller than the nucleus, and that's completely backwards. You could make a case for basically any of these other ones being a fair representation of the space. So if you're looking for the true answer, you would have been able to pick any one of these other choices and you could have been right. Which of these is true? Well, the particles don't have different properties depending on what element they are. The properties of each particle is the same throughout all elements in the universe. Electrons don't orbit like planets around the sun. You could make a case that the larger the nucleus, the more electrons there are, but that's not always true. It would be a good indicator, but it's not always true. So the best answer, and neutrons are always in the nucleus, so that's not going to be right. So the best answer is the last one, because the protons and the electrons are usually the same unless it's an ion. Remember, ions are charged particles, positive or negative, and they're positive and negative because they don't have the same number of protons and electrons. So if they have, most neutral atoms, or all neutral atoms actually, have equal numbers of protons and electrons. How many neutrons would the isotope of sodium have if its mass is 23? So remember, atomic mass equals protons plus neutrons. So the mass is 23. The number of protons, you find that by looking up the element on the periodic table. So the number of sodium is 11, which means 11's protons, plus however many neutrons there are. Well, those two numbers have to add up to 23. So 11 plus 12 equals 23. So it has 12 neutrons, that particular isotope. Any force holding two atoms together is called a bond. There are different kinds, but they're all called chemical bonds. The example of a bond, when you have oppositely charged particles being attracted to each other, those are ionic bonds because you're dealing, again, with ions, positive and negatively charged particles. The attraction between them is an ionic bond. The bond that's formed when atoms contribute or share electrons equally, that's a key thing here. So it's not ionic because they're not actually taking electrons from each other, they're sharing. If it was an unequal sharing, that would be called polar covalent, but equal sharing is covalent bonding. Valence electrons are the outermost electrons, the ones on the highest energy level. Okay, so if you've got 3 layers of electrons, the third layer, the one farthest out, are called the valence electrons. A chemical equation represents what? Well, it's actually, a proper chemical equation would have all of these things. It would show you the reactants, the products, the amounts of each one with the coefficients, and a proper equation has solid, liquid, or gas indicated somewhere in there for the states of matter. In order to balance an equation, you cannot change the subscripts, which would also be changing the chemical formula. So the correct answer there would be A and C, and I guess you could argue that you can't change the channel either, but I was really looking for the things that are actually in the equation that you can't change. What separates the reactants from the products in a chemical equation? That would be the arrow, the purpose of the arrow. The arrow is like the equal sign. It separates the before from the after. And what separates the substances? Well, that would be the plus sign, right? Because if you've got propane plus oxygen, the plus sign tells you, okay, this is one compound and this is another molecule or element. So the plus sign separates each substance in the equation on either side, and then the arrow separates the before from the after. What shows the number of molecules in a reaction? Well, that would be the coefficient. Right? That shows you that there are, for example, 5 H2O molecules. That number there is called the coefficient. It could be atoms of an element too, if it's just something like 3 iron atoms. Right? So that's still a coefficient, but basically it's showing you the number of each substance. And the number of atoms in an individual molecule is from the subscript. So when you have H2O, this is the subscript that tells you that there are 2 hydrogens in this molecule, and the empty or blank subscript here doesn't mean 0, it means 1. Okay, so 1 is implied. What shows the net charge? Well, if there was a net charge that you wanted to show in the equation, you would use that as a superscript. So something like a sodium ion with a positive charge, you'd put a little plus sign up above. That up above part is called a superscript. Or you could have oxygen with a -2 charge. That's the superscript there. The coefficients must always be as small as possible. You want the equation to be the simplest ratio you can get. So sometimes you might end up with a bunch of even numbers, and you could divide them all by 2. If you can divide them by 2 and it still stays balanced, you need to do that. You need to reduce or simplify those numbers. Okay, we're going to balance an equation here. And we want to do, we've got 3 carbon, 8 hydrogen, 2 oxygen, and we have 1 carbon. We have 2 hydrogen, and we have 3 oxygen on this side. So I'm just going to go ahead and balance the equation. You wouldn't put anything in front of the first substance. You would put a 5 in front of the oxygen. You'd put a 3 in front of the CO2, and you'd put a 4 in front of the H2O. So the coefficients are 1, which you don't write, 5 on the left, and then 3 and 4 on the right. Okay, so the question is, what is the coefficient of oxygen? Oxygen has a coefficient of 5 once it's balanced, and water has a coefficient of 4 once it's balanced. Then you end up with 3 carbon, 8 hydrogen, and then you end up with 10 oxygen on both sides. So if you were doing that out, that's what you should end up with. Okay, so now we're going to balance this equation. And again, I'm just going to I'll write out the balanced version. Okay, so the balanced equation is 2 ammonium hydroxides plus 1 oxygen yields 1 N2O plus 2 ammonium hydroxides, and I wrote that but I didn't say it, 2 of those plus 1 of those, 1 oxygen, 1 nitrogen or dinitrogen monoxide, and 2 water, or 4 water rather, because you need 8 hydrogen. 5 waters. Wow. Okay. And then you would need two oxygen molecules. Okay, because then you have 4 plus 4, or sorry, 2 plus 4 oxygens. And then on this side you've got 1 plus 5, so that's 6 on both sides. Okay, so what is the coefficient of the N2O on the right? It's 1, or blank, meaning 1. And the ammonium hydroxide, the NH4OH, has a coefficient of 2 in the balanced equation. And pH, just one question about acids and bases. The pH of a neutral solution is 7. Okay, 7 is neutral. Anything below 7 is an acid. Anything above 7 is a base. The closer you get to 0, the more concentrated the acid. The closer you get to 14, the more concentrated the base becomes. So that's it. You are done with the review, and now it's on to the final exam and wrap up physical science.